So, dear colleagues, today we are holding a joint meeting of two seminars that were launched during the Russia's large-scale invasion to Ukraine. The lecture by Nobel Prize winner in the physics, Professor Ferenc Krausz, is organized as a part of the Kharkiv Chemical Seminar and the Kharkiv Quantum Seminar in collaboration with Kharkiv National University and National Technical University Kharkiv Polytechnical Institute. Professor Ferenc Krausz is a pioneer of Attosecond science. He currently serves as a director at the Max Planck Institute of Quantum Optics and holds the chair of experimental physics, laser physics at Ludwig Maximilian University. He is also CEO and co-founder of the Center for Molecular Fingerprinting, founding director of International Max Planck Research School of Advanced Photon Science, and Center for Advanced Laser Applications. Professor Krausz earned his diploma in electrical engineering with honor from the Budapest University of Technology in 1985. He completed his PhD in laser physics with honor at the Technical University Wien in 1991, where he later habilitated in 1993. His groundbreaking research led to the generation and measurements of the first attosecond light pulses, enabling real-time observation of electron dynamics. This achievement laid in the foundation for attosecond physics, a field with transformative effects for material science, biology, medicine, and other scientists. He has received numerous prestigious honors, including Nobel Prize in Physics, and his works has been cited near 90,000 times, reflecting his profound impact on ultrafast laser science and biomedical applications. He is also a friend of Ukraine who has consistently supported it over the years. This year, for instance, he personally visited Ukraine and Kharkiv and gave a public lecture at Kharkiv National University. And dear Professor Krausz, floor is yours.
Thank you, Professor Chebanov, for the very kind introduction. Good afternoon, ladies and gentlemen, dear colleagues and friends in Kharkiv, in the region of Kharkiv, and anywhere else in the world who may follow this seminar. It is a truly great pleasure for me to be back, even though only virtually this time, to be back after my in-person visit earlier this year. This time now virtually in a joint seminar broadcast to all interested students and faculty members in Kharkiv. Since my visit in March, I followed the news about the war, particularly about the war in your region, with even more interest, and I'm being informed all the time about the terrible attacks of the aggressor with missiles, drones, and obviously more recently even with guided bombs, killing people and damaging all kinds of infrastructure, in particular actually also the energy infrastructure. So I do follow this news with even deeper emotions than before. Since my visit, I feel as if my close relatives and friends would be in danger all the time. And I keep my fingers crossed for the life and well-being of each and every hero of the military units defending the Kharkiv region, the symbols of which actually are just behind me here. I don't know whether the camera does show this to you. I received this gift from the president of Kharkiv National University in March. These symbols remind me every day of this terrible war, every day when I'm entering my office. After having presented the basics of attosecond physics at the national university this year. Now, let's see whether, yes, just early March. This lecture will focus on some intriguing implications of this new field of research, namely on infrared molecular fingerprinting of human blood plasma. My lecture is also a kind of plea for curiosity-driven basic research, which I think is the only human activity that can spawn disruptive technologies which can profoundly impact our life. I think we need them more than ever before to be able to address the greatest challenges of our time. I will come to some of them shortly. At the Ludwig Maximilian University of Munich, the Max Planck Institute of Quantum Optics in Garching, and at the Center of Molecular Fingerprinting in Budapest, which we briefly refer to as Attosecond, we use shortest light pulses and synthesized superoctave optical fields for triggering, controlling, and probing electronic dynamics in atoms, molecules, liquids, and solids, in order to gain ever deeper insight into fundamental electron phenomena on the genuine attosecond time scale. Since 2015, we have been pursuing the question whether these advances may possibly benefit our ability to protect human health, to address one of the greatest challenges humankind faces in the 21st century, which is displayed on this chart, reflecting the correlation between the average number of healthy life years and the GDP per capita in the countries of our planet. In developing countries, newborns have a perspective for a healthy lifespan some 10 to 15 years shorter than their counterparts in developed countries. Almost half of the Earth population, more than 3 billion people, have to accept this gloomy prospect, and are understandably more and more reluctant to do so. We all know the consequences. I guess we all agree that it's more than a moral duty to fight this two-class humankind. Before we can tackle a problem, we need to understand its root. In this case, there are certainly several. In what follows, I'd like to focus on what I believe is one of the main ones. Every year, 17 million people under the age of 70 die of, and actually many more lose their ability to work due to so-called non-communicable diseases, with the four most prevalent ones being cancer, diabetes, cardiovascular, and chronic respiratory diseases. 86% of them in low and middle income countries. Actually, most of these premature deaths would be preventable by early detection and timely intervention. In its absence, the developed countries, such as those of the European Union, spend enormous resources on the treatment of NCDs, and lose enormous resources due to the inefficacy of interventions at a progressed stage of the disease and due to loss of workforce. Altogether, more than 1,500 billion euro, some 4,000 euro per capita, year by year. An amount clearly unaffordable to low and middle income countries. The only chance for changing this unsatisfactory state of matters is preventive care that is able to catch the most prevalent killers in their early stage, when treatment is much less expensive and has a much higher success rate. Equally importantly, this care must also be affordable, certainly an enormous challenge to come up with something that not only simply works, but is even affordable. Fortunately, insight into human organism offers at least a ray of hope. A key hallmark of being alive, homeostasis, keeps our organism within the range of favorable or ideal internal conditions. This crucial rule also applies to the molecular constituents of human blood. They are regulated within narrow person-specific concentration ranges to maintain proper functioning of our organism. Actually, contemporary laboratory medicine is based on this very fact. This led us to the hypothesis that human blood contains the majority, if not all, information needed for comprehensive screening for non-communicable diseases, NCDs. From the perspective of a physicist, the question now almost naturally arises whether physical technologies can possibly access molecular information that is sufficiently comprehensive and sensitive to major NCDs to allow capturing them reliably at an early stage of their development. This is the very question that our team at Kharkiv by München in Germany, by Munich in Germany, and in Budapest and Szeged in Hungary seeks the answer for, with a great deal of dedication. Actually, meanwhile, for a decade. This research started back in 2015. But what is the role of basic research here? Well, a very central one. Actually, it was basic research that has spawned novel physical technologies, such as mass spectrometry-based and nuclear magnetic resonance spectroscopy-based proteomics, metabolomics, and lipidomics, as well as our technology that has been developed in our group, infrared electric field resolved molecular fingerprinting. These modalities together, at least that's our belief and hypothesis, offer the capability of gaining unprecedented amount of molecular information from cell-free human blood. And in the remaining part of my question, I'd like to guide through a research that aims at exploiting this potential. But first, the basics. Consider a molecular variable, be it a spectroscopic feature, like an amplitude in our infrared spectrum of the blood sample. I will tell you more about this in a moment. So consider a molecular variable like a spectroscopic feature, or basically a concentration level of a particular analyte, as we can measure them in laboratory medicine, which is highly stable over time. You see here the green dots depict the value of such a variable. It fluctuates around the mean value, and the mean value V sub I has been indicated here by the dash line, by the green dash line. This usually the range within which this highly stable variable varies over time is substantially narrower than the width of its population reference range, which is shown here by this gray range. Actually, it is this population reference range which you get handed out together with the values of your blood parameters when a laboratory test a clinical chemistry test is being made for you in the framework of some diagnostic procedure. If this parameter is sensitive to a particular disease, the development of this very disease will cause its value to be increasingly up or down regulated with respect to its original mean. In this particular case, this variable is being up-regulated by a certain disease. Eventually, the value quits the population reference range, and actually this is the case when conventional laboratory medicine would ring the alarm bell. But as long as it remains within the gray region, according to contemporary lab medicine, everything is fine. Although, as you see, the three red dots already left your personal healthy range, the green range, but contemporary laboratory medicine doesn't know anything about this because it just doesn't know your personal healthy baseline. So basically only after it leaves this gray area does the person become a patient according to current medicine, and at some point all the investigations, examinations take place, and the clinical diagnosis is being made, and the patient is being diagnosed with a disease that actually induced this change in this particular molecular variable. Unfortunately, quite often at a very progressed stage of the disease, as a consequence, sometimes with poor prognosis, in spite of all therapy opportunities that are around. Had the person-specific mean value and basically the dashed green dashed line and the person-specific reference range, the green stripe around it, had these been known, and the person being followed up in a health screening program, this variable might have been able to set off the alarm bells much earlier, maybe years earlier. In the absence of any symptoms at an early stage, with much better chance for efficient intervention. So this is the basic idea. This is the basic idea behind everything that I'm going to present to you in the following. Quite critical for the efficacy of pre-symptomatic biomarking is the so-called index of individuality, the ratio of the intrapersonal variability, here depicted by W, to the interpersonal variability, here depicted by sigma. Basically, W is the width of the green stripe, and sigma is the width of the gray stripe. And the ratio of the two, W to sigma, is defined as the index of individuality. If your personal reference range, basically the green stripe, is much narrower than the populational reference range, then this index of individuality is a value, it takes a value much below unity, much below 1. And the other extremely important parameter for early detection of a disease is basically the ratio of the disease-induced change in the parameter, which we depicted here by delta, with respect to the intrapersonal variability W, because delta must become comparable or ideally larger than this intrapersonal variability, than the width of the green stripe, to become to place us in the position to actually observe here a change which appears to be abnormal, because normally this value is supposed to vary within the green stripe. And the bigger this ratio at an early stage of the disease, the more suitable this particular molecular variable is for making a contribution to early detection of this condition. We can evaluate the individual-based reference ranges by repeated blood sampling at baseline. So we obviously have to measure this very value several times to be able to evaluate the average value and the spread around the average, which is the width of the green stripe. So we need repeated measurements for that. We all know this in chemistry and physics, of course. Unfortunately, this is not so self-evident in medicine, as it turns out. Of course, from such measurements, we can also determine the usual population reference range, which we always obtain also in cross-sectional studies, clinical studies. From this, we can evaluate the index of individuality. We know both the person-specific average deviation, as well as, of course, the spread in the entire cohort that we include for our study. The other important parameter is what we have referred to as the individual-based effect size, the ratio of delta to the within-person variability W. These are the two key parameters. We need to be able to assess these two key parameters in order to be able to select the best candidates for contributing to a panel of blood parameters that may allow us to provide to ensure early detection of severe conditions. Obviously, these kind of measurements basically repeatedly measure these values, call for a new type of prospective longitudinal cohort study, which we actually dubbed Protecting Health, or I may refer to this briefly, ProHealth, during my talk. The prototypical Protecting Health study was rolled out by our Center for Molecular Fingerprinting in Hungary some 5 years ago. With its repeated baseline, basically 4 times calling back our participants for repeated blood donation, and with its high frequency follow-up afterwards 1 to 2 times per year. Altogether 15,000 participants, out of which we have recruited more than 11,000 so far. This is believed to be the first large-scale study that enables researchers to systematically evaluate person-specific baselines of molecular variables, as well as their response to the early development of prevalent NCDs, such as risk of cardiovascular events, onset of diabetes, COPD, and lung cancer, which will present a sufficient number of new onsets. You see the numbers based on epidemiologic data, the expected number of new onsets over the 10-year observation period, to allow robust evaluation of the accessed molecular parameters' sensitivity to these conditions at early stages of their development, well before they can be diagnosed today. But how can we assess this sensitivity? Well, I told you already that obviously we need to repeatedly measure, we need to repeatedly sample our participants, And we need to perform repeated blood sampling at baseline, which yields both the population distribution, here depicted by the blue distribution, as well as the usually much narrower within person variations, here depicted by the gray distributions of the accessible molecular variables. So I've just selected one variable here to kind of illustrate the concept. Small disease-induced changes in the accessible molecular variables are often buried under the broad population distribution. Imagine that the disease causes just a small fraction, maybe 10 or 20% of the width of this blue distribution. You would hardly detect it. However, if we would be able to observe the much narrower within person distribution, then this would cause a much bigger relative change in that distribution. So how can we get this? Actually, thanks to these repeated measurements, we can evaluate these usually narrower within person distributions. And this allows us to sort those individuals, the values of which are distributed around the same mean value. And this is shown here by this gray distribution. So basically they do not include only one person, but if we have a large cohort, there may be quite a few persons in this cohort whose mean value is roughly the same, and around the same mean value they have little deviations in repeated samplings, and these are the gray distributions. So knowing these distributions of these individual groups, we can now narrow the healthy baseline by shifting all these gray within person distributions such that their mean values coincide with the, no, it doesn't seem to work. Let's see. Yes. That their mean values coincide with the populational mean. The resultant average intrapersonal distribution is usually significantly narrower than the population distribution, and hence very obviously more susceptible to small changes over time. For instance, due to healthy aging. As sketched here for a hypothetical variable that is insensitive to the developing prevalent NCDs, but does vary with increasing age. This aging might cause maybe a slight shift of this distribution. This is just, I'm just hypothesizing, just for the sake of argument. The more important part is coming now. What happens if the variable is actually sensitive to a developing common condition, which, as I pointed out to you before, appears in a significant number in such a large cohort. For instance, diabetes, several hundred new onset cases among these 15,000 participants over the years. So let's suppose that this very variable is sensitive to this particular condition already at a very early stage of this condition, way before the condition is actually diagnosed. And let's suppose that this very variable is upregulated by this prevalent condition. What does this imply? Well, with the progression of time, a tail is growing out of the average interpersonal distribution. A certain fraction of the persons start developing this disease, and the value of those persons is being upregulated, which leads to an outgrowth of basically outgrowth from this narrow distribution. In this particular case, in the case of upregulation, to higher values. And this outgrowth, this increasingly extending wing, is just growing and growing with the progression of time. It is extremely important to note and to realize that observing these states as a signature of disease-induced upregulation of the selected parameter does not rely on the knowledge of diagnosed cases. I don't have to know the diagnosis yet, because the diagnosis is not even in place, but it's no problem. I will see if there is a sufficient number of new onset cases, and if this particular variable is sensitive to that, like it is being upregulated at an early stage of the disease, then this is expected to happen. And I don't have to know the diagnosis of those people. This is extremely important because obviously, if I want to capture early indications, then the disease, the diagnosis is in most cases is not even in place. Therefore, long before all new onsets are diagnosed towards the end of the 10-year study period, we shall be able to identify the most promising spectroscopic, proteomic, metabolomic, and lipidomic variables with a low index of individuality and high individual-based effect size for one or more prevalent NCDs as candidates for signaling the risk for or onset of new conditions in a hopefully cost-effective and highly sensitive fashion. Why cost-effective? Because instead of measuring the thousands of variables accessible, we shall be able to optimize the underlying omics technologies for those sets of variables that meet these conditions, these two conditions, low index of individuality and high individual-based effect size, which we will be able to measure thanks to the blood samples we are collecting in the framework of this Protecting Health study. Well, so far so good, but let me just make a big step backward and try to put this into context and address the question how we actually ended up working on this. On the turn of the new millennium, when our group at the Technical University of Vienna produced the first isolated pulses of attosecond light, actually the briefest man-made event, with which the fastest processes outside the atomic core, the motion of electrons, could be captured and reconstructed in slow motion replay, exemplified here by the electron migration in organic molecules. Electronic motions are of utmost importance for our life, for our biological and modern life likewise, and probably that's why the Royal Swedish Academy found the ability to capture them worthy of this, well, a couple of years later, still unbelievable recognition. The attosecond metrology we originally developed for tracking electronic. Have you actually seen my video? Because I just got a message that maybe the video was not playing properly. I hope that
everything was okay.
Yeah,
yes.
Wonderful. Thank you. Okay. So the attosecond methodology we originally developed for tracking electronic motions has also proven capable of sampling the oscillation of light waves, which also takes place essentially on the same attosecond time scale. Well, this solution, like originally the laser, this solution was also looking for a problem and found it some 15 years later by capturing the molecular vibrations induced in human blood in real time. Imagine we expose cell-free blood to an extremely brief infrared laser pulse, just one single oscillation period ideally, which brings the molecules in vibration by exciting their infrared active vibrational modes within the spectral band of the excitation. The vibrating molecules in turn emit coherent infrared light in the wake of the excitation. The vibrating molecules, of course, actually the coherence of these vibrations decay quite fast, and this process ends a few picoseconds after the excitation. But if the excitation is short enough, and this is obviously the case, if it consists only of one oscillation period, then basically it ends after almost completely after a couple of 100 femtoseconds by an exponential decay of the amplitude of the excitation pulse. And there basically a couple of 100 femtoseconds after the excitation peak, a kind of window of darkness opens up where there is no light anymore other than the infrared light that is emitted by the coherently vibrating molecules. And basically we can measure then from this time point on, here basically indicated in the frame, we can measure the oscillating electric field in this signal emitted by the molecules by means of attosecond, femtosecond metrology. Actually, since the oscillations of this infrared light in the mid-infrared take place on several femtoseconds, a pulse duration for capturing these vibrations of the order of a few femtoseconds is sufficient. So we don't need actually attosecond duration pulses for this, but nevertheless, thanks to the outstanding signal to noise ratio, which we can accomplish in our measurement technology, we can measure the waveform with attosecond precision. For instance, we can measure the zero crossings of the field truly with a few attosecond precision. So I think it's fair to say that it is, in spite of the use of few femtosecond light pulses, it is an attosecond precision, not necessarily resolution, but precision spectroscopy. We have dubbed this very signal the infrared electric field molecular fingerprint of the blood sample because it is highly specific to individuals. It is also sensitive to health disease transitions, which tend to change many of the concentration levels of the hundreds of thousands of molecules contained in our blood plasma sample. And changing concentration levels also change the overall fingerprint signal because different molecules emit different fingerprint signals. Here you see a few examples. For instance, the frequency spectrum of infrared fingerprints for some proteins. Here some metabolites. The slightly differing person-specific concentration levels of these molecules lead to small but discernible differences between the infrared fingerprints of individuals, as shown by this family of traces here. These fingerprints have been measured by conventional Fourier transform infrared spectroscopy, the ones that I've just showed you. And this technology, this type of spectroscopy has been around and advanced for decades. However, its sensitivity is still limited by the technical noise, here indicated by this white stripe, by the technical noise of the excitation source, which determines the smallest change in the molecular concentrations and composition that can be detected. Field-resolved infrared spectroscopy overcomes this limitation by, as I just explained you before, by isolating the molecular signal from the excitation. We hit the molecules very quickly and leave them alone and just listen, or actually in this case watch with our detector, and they can measure the signal from the molecule in a background-free fashion. This is supposed to offer access to smaller changes in the molecular concentrations and therefore a greater variety of molecules, the concentration level changes of which we can possibly detect. Decade-spanning efforts by my colleague Alexander Weigel and his team has spawned electric field resolved infrared spectroscopy, which overcomes this limitation, as I just mentioned, by isolating the molecular signal. Latest generation of this very technology, which is actually already the third generation, offers within a sub-millisecond duration scan. So basically, within a fraction of 1 millisecond, we can scan the gate pulse through the molecular signal oscillations and record a complete trace. And within such a sub-millisecond scan, we can record the electric field with a signal-to-noise ratio of the order of 7,000. Of the molecular signal repetitively produced at a 25 megahertz rep rate. And as you of course may guess, we repeatedly do these measurements over a few seconds at least, or a few tenths of seconds. And then with the square root of the number of repeated measurements, this signal to noise ratio will further improve. So basically, within a few tenths of seconds, we can repeat these measurements by something like 100,000 times, which means that another 2 to 3 orders of magnitude increase of the signal-to-noise ratio, way above 1 million. And this is in the electric field. So if you would square this in the intensity, this means a signal-to-noise ratio of 12 orders of magnitude. So the metrology is truly sensitive. The fingerprint signal is expected to change whenever emerging abnormalities change the sample's molecular composition. And we have verified this meanwhile for a number of chronic conditions, including 4 different types of cancer: lung, prostate, breast, and bladder cancer. These curves on the left-hand side show how the true positive rate can be increased at the expense of increasing number of false positive by varying the discrimination threshold in the classifier algorithm, which we have trained with a fraction of the samples from cases and from suitable controls. The overall detection efficiency can be best characterized by the area under this curve, the so-called AUC value. As an example, I show here the electric field molecular fingerprints of patients diagnosed with non-small cell lung cancer and well-matched healthy controls, 470 each. 470 cases diagnosed with non-small cell lung cancer from stage 1 to 4, all stages from early to progressed metastasized stage 4, as well as 470 non-symptomatic well-matched controls, well-matched in terms of significant confounders or covariates such as age, such as sex, such as body mass index, and of course, in this particular case, smoking status. The conspicuous differences between the red and blue fingerprint traces open the door for training an algorithm for detection of lung cancer, of non-small cell lung cancer. To this end, we use 90% of the measured infrared fingerprints for training the algorithm via machine learning, and the remaining 10% for testing it. The diagram on the right-hand side shows the classification efficiencies, the previously defined AUC values of the resultant algorithm, evaluated for different stages of the disease. Here, only for the relatively early stage resectable non-metastasized stages from stage 1 to stage 3A, with relatively good prognosis. The results are promising, but offer room for improvement. We can quantitatively analyze these differences in terms of some discrete variables, such as the gaps between the adjacent zero crossings of the oscillatory signal, the so-called half-cycle gaps, or the areas below and above the half cycles. In both cases, two discrete variables per cycle are evaluated in line with Nyquist's sampling theorem. Here you see the mean and the standard deviation of the half-cycle gap spectroscopic markers. In this particular case, more than 350 of them. Actually, the signal goes on quite a bit further, but the signal-to-noise ratio is rapidly decreasing. We are still working on this and hope that we very soon will be able to extend this number to 1,000 and even beyond. But right now, we focus on these 350 spectroscopic variables. In this particular case, these half-cycle gaps. And of course, we can measure the same variables also for the actual cases. The gray shaded area depicts the spread. But what is truly important, what really matters, is actually the average change, or are the average changes induced by the disease with respect to the average of controls. So basically the difference between those two variables that I showed you previously for cases and controls. This is case minus control for each variable. In some cases, obviously the disease increases the signal. These are depicted in red. In some other cases, the disease reduces the signal. In this case, it's depicted in blue color. And importantly, the spread of controls is also shown here by the gray shaded area. So you see that this spread is quite big as compared to the disease-induced signal. And therefore, it is quite natural that it is a bit tricky to actually detect the disease by use of these signals. And actually, this very diagram also is, I think, a very nice demonstration of the power of artificial intelligence. The disease induces relatively small changes in the range of half a femtosecond shift in these half cycle gaps, plus or minus, typically half a femtosecond, in some cases maybe 1 femtosecond, but in very few cases, and in many cases even much less than half a femtosecond, as compared to the spread among the healthy controls, which obviously amounts to typically way above half a femtosecond. So, within this spread, these tiny disease-induced signals are obviously sufficient that the artificial intelligence is able to find systematic changes in the patterns between the two different signals from cases and controls, systematic differences which are sufficient to train an algorithm for recognizing these differences, with the efficiencies shown here, AUC efficiencies shown here on the left-hand side for different stages. So stage 1 plus 2, AUC 70%, stage 3, 87%. Importantly, please take a look at the left-hand side, which shows the ratio of these disease-induced changes, the delta, with respect to the populational spread. This is kind of a similar effect size that I introduced before, but in this case, the disease-induced effect is not related to the within-person spread, but to the populational spread. And that's why I emphasize here, this is the so-called populational-based effect size. But what is important, there is a clear correlation. The bigger the effect size, the better the algorithm performs, which I think we all expect. Yeah, so the bigger relative effect the disease causes with respect to the spread of the references, the more easily the algorithm will recognize this as being caused by the disease. And this manifests itself in the increasing AUC values for increasing effect sizes for progressing stages. So obviously, if we want to improve our algorithm to detect the disease, in this particular case lung cancer, with higher efficiency at an earlier stage, we need to boost the effect size. But how to boost the effect size? The disease causes this effect, so there is nothing much we can change on the delta, which is the numerator of this simple formula for the effect size. But there is also a denominator in the expression, which is the spread. And the spread here is the populational spread, which is pretty broad because we are very different. Even whilst we are healthy, we are very different. And this differences reduces, unfortunately, this effect size. And this compromises the ability of the algorithm to recognize this disease. So what can we do? What can we do? Well, we should try to increase the effect size. The delta, there is nothing much we can do about this. But we could perhaps increase the effect size by reducing the spread of controls. How? We have seen this before, by self-referencing. Instead of referencing the disease-induced basically fingerprints to a number of fingerprints taken from a healthy population, try to reference it to the fingerprint of the same person before she contracted the disease. Of course, this is possible only by longitudinal follow-up, but this is exactly what we are doing in our study. So obviously this spread could be significantly reduced, provided the within-person variability is smaller than the between-person variability, or in other words, the index of individuality is smaller than 1. And here is the first evidence from a large-scale study from our H4H study that this is indeed the case for the infrared spectroscopic variables. Here in the spectral domain, you see the spectral amplitudes of our infrared fingerprints in the wave number range from less than 1,000 to more than 3,000 wave numbers. And you see that the intrapersonal variability is at each and every wave number smaller, even significantly smaller than the interpersonal one. in some ranges up to a factor of 3 smaller, in most at most wave numbers at least a factor of 2 smaller. So obviously, if we would manage to take the fingerprints from the same person before she contracted the disease as a reference, we would have the chance to improve the detection efficiency and be able to observe the disease with higher accuracy at an earlier stage. We cannot provide a firm experimental evidence for this yet because we don't have a sufficient number of diagnosed lung cancer cases our study, but we can do a computers or could do already a computer simulation. We used the disease-induced signals obtained in our cross-sectional study, which we dubbed Laser for Life, by the way, which we do here in Munich, Germany. We took basically the disease-induced signals as obtained from this cross-sectional study. These are the differential sort of signals that I showed you before. So these are experimentally obtained. And take the narrowed average interpersonal distributions from the H4H study from the longitudinal follow-up to simulate the effect of reduced spread of references on the lung cancer classifier. And here you see once again the classification efficiencies from the cross-sectional study. And we now assume that the interpersonal variability displayed by the spread of blue traces is replaced by the intrapersonal variations of the H4H fingerprints. We may guess that the algorithm will have a much easier job to distinguish the red traces, the traces of the cancer patients, from the blue traces. And this indeed is confirmed by our numerical simulations, resulting in a dramatically improved classification efficiency of early stage lung cancer, using actually the cancer-induced infrared signals we can measure today. So this is a first indication of the power of longitudinal follow-up for precision prevention care. The capacity of EMF, electric field molecular fingerprinting, to capture different types of cancer prompted the question whether the method may be capable of doing more than detecting merely a single pre-selected condition. The first encouragement was provided by a recent study conducted in collaboration with researchers from the Helmholtz Centrum in Munich, in which 4 common chronic conditions could be detected in a single measurement. And perhaps even more remarkably, the absence of all 4 conditions in the healthy subgroup of the cohort could be also verified with an impressive AUC of 90%. This study actually highlights the general focus of health monitoring, the reliable exclusion of ever more chronic conditions for early warning preventive care. The more diseases we wish to be excluded, the more information we need to collect from human blood, very obviously. And now, therefore, the question arises how we can possibly rigorously quantify this information carried by molecular variables. Repeated measurements of the variables in a longitudinal follow-up of individuals offers also for this a unique opportunity. Here you see the prediction accuracy with which we can identify 1 among 4,500 individuals with an algorithm trained with 4 repeatedly measured data sets and tested on the 5th one. we have used two different types of data sets, a clinical chemistry panel consisting of 27 commonly used analytes in laboratory medicine. This is the clinical laboratory panel indicated by the red red dots. And infrared fingerprints, in this case acquired by conventional Fourier transform infrared spectroscopy. As you see, the classification based on the infrared fingerprints increasingly outperforms, these are the blue dots, increasingly outperforms the classification using the 27 analyte clinical chemistry panel. And quite interestingly, the combination of both actually yields a remarkable identification efficiency exceeding 90%, even for more than 4,500 individuals. This means that taking together these two sets of data, we can identify more than 4,000 people out of the 4,500 currently. But what is perhaps even more important, and this is what I truly would like to emphasize, that these values naturally yield the Shannon entropy, or actually a lower bound on the Shannon entropy of the data set, without making any assumption regarding the correlation between different variables in the data set. Identifying 4,500 persons requires some 12 bits of information. And with the combination of the two data sets, we come quite close. We very closely approach this value. And maybe the data sets actually contain significantly more than even 12 bits, but we don't have enough individuals at the moment to directly measure this. That's why I'm saying that basically this sets a lower bound on the information, Shannon information that these data sets deliver about human blood. So the main thing is, thanks to longitudinal follow-up, we have now a most powerful approach to determine the information content of any set of health parameters repetitively measured via follow-up. It seems that conventional IR spectroscopy works pretty well. This prompts the question whether resolving the electric field offers any advantage in the acquisition of biological information. To address this question, we have just very recently completed a pilot study, actually really just a couple of weeks ago. So these are everything unpublished results, not even written up for publication. This time, we included 75 individuals with 4 blood samplings, each of them. And we trained the person identification algorithm with 1, 2, and 3 fingerprints obtained by either FTIR or laser-based EMF measurements. And here you see the accuracies with which the 75 participants could be identified by the classifier trained by FTIR. These are the blue symbols, and by EMF, these are the red symbols. So obviously EMF significantly outperforms the best FTIR. This is really the best FTIR that is available on the market, in spite of the fact that the EMF instrument covers less than half of the optical bandwidth of the FTIR instrument. Here, this graph shows actually the fraction of the entire spectral range that is accessed by state-of-the-art FTIR. Not even half of that was accessed in this particular comparative study. And yet, even accessing just this fraction of the entire FTIR spectral range, we could outperform FTIR spectroscopy, which is, I think, more than promising. Next generation EMF instrumentation, which will be commissioned shortly. Actually, the device is up and running. We are just performing the final tests, which will take another couple of months before, hopefully early next year, we can indeed start the routine measurements of blood samples with this so-called third generation device. This will be removing this shortcoming by covering the entire range of next neighbor vibrations, all the way from 20 to about 100 terahertz, and correspondingly we'll have a significantly increased number of half cycles that we capture, and a corresponding increase in the number of variables. So we hope that this will yield more than 1,000 variables, commensurate with the number of half cycles in the free induction decay signal emanating from the coherent molecular vibrations. But the molecules may have to tell us even much more when being excited by the sub-femtosecond deep UV transients that our group recently generated and also sampled up to 2.5 petahertz. This feat now may pave the way for extending vibrational to actually vibronic fingerprinting, vibronic standing for vibrational and electronic fingerprinting, for capturing molecular signals with frequencies extended all the way from several terahertz to several petahertz. These findings encourage us to expand the scope of our so far bilateral cooperation between CMF in Hungary and LMU in Germany to a global initiative, which we dubbed Protecting Health. In Hungary, the prototypical ProHealth study is underway. In Hong Kong, it is due to start soon at the University of Hong Kong, and discussions about further nodes in the network are underway. Our goal is to establish a global network of standardized Protecting Health studies to collect some 1.5 million blood samples over the next 10 years across diverse ethnicities to provide access to NCDs with lower incidences and also with lower incidences, and allow us to gain evidence of the universality of the integrated molecular phenotyping approach. The Protecting Health partners will contribute blood plasma samples and accompanying clinical data for training the proprietary ProHealth screening algorithm for early detection of the most prevalent non-communicable conditions. This will occur in 2 phases. First, we aim to discover the blood parameters, including several spectroscopic, proteomic, metabolomic, lipidomic variables with highest diagnostic power for the risk and onset of common NCDs. Subsequently, we use them for training the algorithm, the health screening algorithm for capturing abnormal deviations from healthy baseline, and with the accumulating number of diagnoses for diagnosing the condition behind the deviation. With this algorithm, we aim at establishing a cost-effective universal screening platform for the major non-communicable disorders, including cancers, cardiovascular, respiratory, metabolic, and eventually, hopefully, even neurodegenerative disorders. My long-standing colleague, Michael Schickmann, summarized our vision as follows. Imagine a tool that could catch issues before they become significant problems, like a sensitive radar, but one that is affordable to everyone and is fast and easy to use to detect irregularities well before individuals get symptoms or would even think about seeing a doctor, to nip potential health hiccups in the bud, promising help to keep us on the road of well-being. Thank you very much for your attention.
Thank you very much, Andrei.
Thank you very much, Professor Krausz, for this wonderful lecture and very inspiring. So let us switch to the questions and answers session. Please, participants, raise your hand, virtual hand, if possible. We will pass microphone to you. Well,
May I
still,
ask you?
yes, please, Galina.
Hi, really inspiring
Hello.
lecture.
Thank you.
I worked in a nanosecond laser and for the induced force microscopy. We studied extracellular vesicles in terms of and identify where is a cancer-related one and healthy one. So, have you worked with extracellular vesicles to try to identify cancerous or non-cancerous one? I just wonder, is there any potential in this area?
Really. Yeah. Thank you for the question. Not really. Of course, we are aware of all those efforts that are using other components of human blood to capture cancer, specifically cancer, in a non-invasive manner. For instance, also cell-free DNA that is around, which is excreted by tumorous cells and which make it into the bloodstream. And there are, of course, also other possibilities like the one you mentioned. We have not been involved in that. Actually, our method potentially is also sensitive for DNA, but DNA is present in human blood at such low concentrations that we just cannot detect it with our method. So basically, we have to live with what current technology, that the ones that we have at our disposal can access and see how far we can get with this. And of course, we are also open for collaborations and if collaborative partners have access to other variables in human blood that may provide information about the emergence of diseases, then we are more than happy to team up with them and to combine these technologies and see whether the combination actually has any added value. So we are very open for that, but we have not been involved specifically in other research in this direction.
Actually, we use a nanosecond laser for the protein secondary structure identification. So we use protein secondary structure to identify the cancerous and non-cancerous, because it is known that like cancerous cells has a more beta turn structures rather than alpha helix structures. So that's why we basically using the IR
But you do this
spectroscopy.
directly on the cancerous. You do this directly on the cancerous
Yeah,
cells, right?
yeah.
So you have to basically, this you can apply at a stage when basically the tumor has already been found in the body, and basically via biopsy,
we use cells
have been extracted. Yeah.
And then mount
I guess this may be very helpful when it comes to actually stratifying which kind of subtype of cancer this particular case represents, because this is very important for decision making about what kind of therapy offers the biggest chance for efficiently fighting the disease. We are focusing to actually a much earlier stage when basically we have no idea whether we are even ill, but we would like to capture it at that stage to actually make sure that we capture the disease at a stage way before it has the chance to metastasize. Because usually any type of cancer, once it has metastasized, the prognosis is quite poor.
Yeah. The idea is to find out biomarker of cancer. That's the idea.
Exactly. Yeah. And of course, for that, you cannot possibly consider biopsy, right? Because no healthy person without symptoms would subject themselves to such an invasive procedure. So for health monitoring at the stage when people believe I'm completely healthy, it can only be successful if the procedure is minimally invasive, right? Which applies to a venous blood draw, but unfortunately it doesn't apply for a biopsy.
We actually extract the extracellular vesicles from blood and mount them on the surface
I mean,
of
that's
mica.
of course, that's an option. That's an option. That's an option. I mean, to look at them in human blood, that's certainly an option. Right. Right. We haven't done this yet. Potentially we can fingerprint also whole cells. And my colleague Michaela Schiegmann is working on that with her team. As you can imagine, this implies quite a few technological challenges to bring the individual cells precisely and efficiently into interaction with the focused infrared laser beam. But they are working on that, and there will be solutions for that. It just takes some time. So potentially this might be a future avenue. You are right.
Thank you.
Thank
We
you.
have the next question from Alexei, please. I think you can spell your question. Yeah.
Thank you very much for such interesting presentation. A few questions, if you mind. First, regarding the probably continuing a little bit the previous one. It's about the region that you are currently is out of reach for you, so above 2000, say, centimeters, where probably all these signs of helicity in macromolecules and also hydrogen bonding features can be found. So are you going to investigate when expanding into this region with the same precision, I mean, with the same step as for the fingerprint region, or basing on a different approach?
When we extend into which region, I'm not sure I precisely understood your question.
Above 1500. Above 1500.
Of course. I mean, the resolution, the spectral resolution is exactly the same up to higher frequencies. So actually, I think it's a very nice the fact that we measure our signal directly in the time domain gives us the chance to provide a very simply way of actually assessing the spectral resolution. The relative spectral resolution is just 1 over the number of cycles that I can measure with good signal to noise in my molecular signal. If let's just assume I can measure 1000 oscillation cycles in the signal before it disappears below the noise level, then this would mean a relative resolution with a relative bandwidth of 1 over 1000. So basically, at a value of 1500, 2000 wave numbers, this would mean that our spectral resolution, if we just Fourier transform this temporal signal just into the spectral domain, then basically my spectral resolution would be somewhat around 1 wave number. Which is more than enough, given that unfortunately the features are in the spectral domain quite a bit broader due to the unfortunately relatively brief coherence time. So we have unfortunately pretty broad features, and we do not have a lot of structures. I could perhaps just go back to this just to remind you how typical a spectrum looks like. So these are infrared spectra of proteins. So you see the features are pretty broad and poorly structured, and differences are subtleties, really just in the shape of these peaks, and that's what we try to capture, and that's where the information is being delivered. In the case of smaller molecules, metabolites, there are more features. It seems that the coherence time is longer. So basically the spectral width, the peak spectral width here are significantly narrower, factor of 2 to 3 narrower than in the case of proteins, which means that the coherence decays in the small molecules on a longer time scale. And we believe that this is due to inhomogeneous broadening in the large molecules. So basically, these signals come from next neighbor vibrations. And in a protein, we have basically many next neighbor modes of the same kind, CH, CA, double bonds, OH, and so on and so forth. But their chemical environment is slightly different in the big molecule, right? And these different chemical environments may cause kind of chemical shifts, which broadens the spectrum. So this is what I call in the language of spectroscopy an inhomogeneous broadening. And this, of course, shortens the coherence time. And that's why, yeah. Sorry.
Yeah, if you mind, I have a little comment on this. So these region above to 2000 is not about an individual vibrations. They are no longer bone stretching or angle or so on. They are mainly related to in specific interactions like hydrogen bonding. They are very sensitive to a packing, to this helical structure. That's why you don't need that large resolution actually in this. So probably you could just take a wider frame for, you don't need one inverted centimeter to get actual information in this region. But this region can give you unique information about packing of molecules, which is
yeah, but you know, in our measurement technology, this comes from free, right? I mean, we measure this coherent signal, let's say, over a time window from basically the excitation to, let's say, 10 picosecond. I'm just making it up, right? This is the time window, 10 picosecond. So that means that I have an oscillatory signal over a time window over a period of 10 picoseconds. So basically, my spec, this just delivers me the spectral resolution of 1 over 10 picoseconds, right? Or in wave number units, this would be kind of 1 wave number. I don't have to make any efforts for this. This comes for free, right? So I, of course, before I go and ask the artificial intelligence to help me and to recognize differences in the two patterns, I would not like to eliminate any information that these signals may contain. But I just take the full information, the full signal, and show it to the artificial intelligence and ask kindly, I'm very kind to the artificial intelligence, I have a high regard for it, and ask it to actually try to undertake all possible efforts to recognize systematic differences between the two classes of patterns, one coming from the diseased cohort and one coming from the healthy control cohort. Yeah, that's it. So it's nothing magic. We don't really have to do at this point a lot of digging deeply what kind of molecules, what kind of bonds are behind those spectra or behind those signals for the specific purpose, for being used for medical purposes. The only thing that matters is that there is a robust correlation between a certain pattern and a certain health condition. If there is a robust correlation, and I see this correlation in many individuals suffering, being diagnosed with the same condition, that in all these individuals, or in a majority of them, there is a certain change which I can correlate with the presence of this particular disease in their body, this is actually sufficient for being used for medical purposes. And this is the very basis behind MRI, for instance, right? The whole magnetic resonance imaging, which probably no one in the medical community would question how important it is, how important role it plays in medical diagnostics, is about pattern recognition, right? Basically is based on this correlation. If a tumor is growing in my brain, basically the tumor part, the molecular composition is changing, and this changing molecular composition changes the radio frequency signal that my MRI device is detecting in a special way. And in that particular region, this signal looks somewhat differently from the signal coming from the healthy regions of my brain. And this is the basis for delivering the images, which serves as a diagnosis for brain cancer by means of MRI. MRI doesn't provide any information about the molecules, about the molecular composition, what kind of molecules are behind those changes, nothing, right? It's just that there is obviously a robust correlation between changing those radio frequency signals that is being observed in MRI and the appearance of a particular condition. And this applies to 100% the same way here. It's just another spectral region. We are doing pretty much the same as nuclear magnetic resonance spectroscopy is doing, except that we are not doing this in the radio frequency domain, but we are doing this in the infrared spectral domain at a billion times higher frequency.
Thank you.
May I ask a question?
We have,
Of course.
As far as I understood, your main assumption consists of almost equal intensity of each periodic signal. Is it true? If you have
no, it doesn't have to be. It doesn't have to be. Actually, you see that for instance, on this very graph, you see that the different spectral components, for instance, in the molecular signal coming from these molecules. So basically, what you see here is the spectra of the molecular signals that are generated by this molecule, by these molecules, after being hit by a very short, very broadband infrared laser pulse, right? Which covers the spectrum, basically this entire spectral range, so that to ensure that at each and every wave number featured here, basically there is a component in the excitation pulse so that it can kick in these vibrations, right? And we do it with a very short pulse and then leave the molecules alone. They keep oscillating. And then if we just analyze the spectral content of those molecular oscillations, that's what we have, right? That's what is shown here. And you see that in each of these molecules have frequency components where they oscillate very strongly. Of course, these are the resonances. These are basically the eigenfrequencies of the vibrations, right? There, the molecule takes up a lot of energy from the excitation. Correspondingly, it can afterwards oscillate with a high amplitude, as shown here, like in the case of lactic acid at 1750 wave number is a big peak. But if you go away from that and go to maybe 1500 wave number, the same molecule just doesn't produce almost any signal, right? Because there is no resonance there. The molecule cannot take up any significant energy at that particular frequency, and therefore cannot also give back any energy at that particular frequency. So the quick answer to your question is that the different components, spectral components in that molecular signal can have very different amplitudes.
Okay, thank you.
And we have perhaps the last question from Halina Krapchuk. please. Unmute yourself.
Actually, it's Igor Komarov, it's a computer of Kharkiv. Thank you very much. Thank you very much, Professor Krausz, for your wonderful lecture. I've been on your lecture in Kiev in March, where you delivered
thank you.
Basics physics. And now it's so exciting to see the application of this basics. It's very encouraging, especially for young people. Actually, my son is also watching you and also expresses
great
excitement. Yeah.
Also interested in physics?
Yeah, in mathematics and physics.
Very nice.
My question is, Professor Krausz, how did you achieve terahertz region? I mean, this is very interesting region, and which could provide new opportunities for your research because it contains a lot of information about motion of biological molecules. That could be a new frequency window and would be also exciting. Was it by applying new technology, or is it the same technology?
Yeah, thank you so much. This is an excellent question, and it puts me in a position to actually address something that I didn't have time for during my talk. So you are absolutely right. The low, I guess you mean the low terahertz region, right? Because I mean this region is also terahertz, but this is pretty high terahertz, tens to 100 terahertz, right?
Yeah, that's right. That's right.
But you are right. Potentially, we could extend this down to a few terahertz, and at those low terahertz frequencies, we could potentially access information that we may not be able to access at these relatively high frequencies. And this information relates to the vibration of the molecules, basically the low frequency vibrational modes, which are not next neighbor, where just a couple of atoms are participating, that are being connected by a chemical bond, but these are vibrations in which whole fractions of the molecule oscillate as a rigid body. And the frequency of this is naturally much lower because the mass involved is much bigger. So therefore, the eigenfrequency of the vibration, it's inversely proportional, of course, to the mass. The bigger the mass, the lower the frequency. And that's why in order to access them, to actually excite them and to make them oscillate and then radiate in a similar way as we see it here, we need low terahertz radiation. Why we are interested in this? Because unfortunately, these next neighbor vibrations, which we can address now, tell us little about the overall structure of large molecules. So if a protein is being folded differently, this doesn't change the number of CH bonds, the OH bonds, and all these things at all. And therefore, the fingerprint that we can currently access at the high frequencies probably doesn't change substantially. Maybe quite a little bit due to some effects, some hydrogen bonds and things like that may change if the whole overall structure, the secondary, tertiary structure of proteins change. But these are very subtle changes. So probably the low frequency vibrational modes would probe these kind of changes where a protein changes its structure much more efficiently. So therefore, we are very motivated to look into this, and we have started doing this actually a while ago. And the nice thing about this laser-based approach to infrared spectroscopy is that the very same laser device we start out from, a femtosecond laser, is via nonlinear effects suitable to generate not just this relatively high frequency infrared light in the tens of terahertz region, in the mid-infrared, but potentially this can also produce low terahertz radiation. Of course, in other materials and other potentially other processes, although processes in sometimes is the same, actually difference frequency mixing, optical rectification, kind of the same nonlinearity, Chi2 nonlinearity, as we are using here for generating the mid-infrared radiation. So basically, the same toolbox that femtosecond technology offers us allows us to extend the current spectral coverage quite naturally to the low terahertz frequency region, and we are working on that. So thank you, very good question.
Thank you very much. Actually, we are developing low terahertz emitters, and probably this would be interesting to.
We would be very, very interested in that. If you have any good idea how we can, because unfortunately the conversion efficiency as we move towards lower and lower terahertz frequencies, unfortunately the conversion efficiency from the near infrared, which we start out from with the laser, is very rapidly declining. So if you have any idea or any experimental evidence or concept that might improve the situation in terms of conversion efficiency, we would be very much interested. Please just get in touch with me, and we are very interested in any kind of collaboration.
Okay, thank you very much.
Thank you.
I'm sure that many of us have more questions, but unfortunately time flies by. So thank you all for wonderful conversation and pleasant. It was a real pleasure to listen. And
I thank you, of course, for your interest and for letting me speak so long. It got a bit long, but thank you.
That was very pleasant and insightful. And we have one more extra event. So I would like to pass microphone to Vice Rector of Research and Teaching at Kharkiv University. So please, Boris Samorodov.
Dear Professor Krausz, dear colleagues, on behalf of Kharkiv University, I would like to sincerely thank you, Professor Krausz, for your time and for your support of our university, our academic community, and Ukraine. Your visit today and your lecture mean a lot to us. You show us that the global scientific community stands with Ukraine during these difficult times. Your willingness to share knowledge, to speak with our students and scientists, and to engage in open dialogue while our country defends its freedom is deeply appreciated. You remind us that science and human values unite people everywhere. And it is a great honor for us today to award you the title of visiting professor of Kharkiv Kharkiv National University. And if you don't mind, I will show you signed by our rector, Professor Tatiana Kaganovska, and I think we will send this certificate for you. And this title is not just a formality. It symbolizes our shared values, mutual respect, and your belief in the potential of Ukrainian science and education. We are proud to welcome you as a visiting professor of Kharkiv University. Thank you for your friendship, inspiration, and solidarity with Ukraine. Thank you very much.
Thank you very much, Professor Samorodov, dear Vice President. I'm moved, and I thank you very much for this recognition. I have to tell you that I felt a lot of sympathy for your heroic fight against this brutal aggressor already before I visited Ukraine, but this sympathy grew exponentially upon the visit, during the visit, seeing and experiencing the attitude of Ukrainian people, how they arrange themselves with this situation, and how they keep together and defend their country and defend at the same time whole Europe. So I try to do everything that I can with my modest influence and my modest possibilities to support this heroic fight. You might have heard or not, I don't know. I have actually with my team we have set up a website called peaceforeuropa.org, where we actually published the petition of the 131 Nobel laureates that I brought with me upon my visit that time, and invited all European citizens to actually add their vote to their petition to be able to increase the pressure on European leadership to release the Russian assets that are being stored in Europe for rebuilding Ukraine and for providing these resources to Ukraine. On the one hand, for strengthening the country in your heroic fight against the aggressor, and also start rebuilding the country as soon as possible. So obviously, first there are first signs that the European leaders are indeed undertaking actions here. In the first place, our Chancellor here in Germany took an initiative, and this is being very intensively discussed these days. And I'm keeping my fingers crossed that with a very positive outcome for Ukraine in the very near future. So thank you very much, and I take this also as a kind of duty that this a very pleasant duty that this imposes on me, this recognition, and I would like to feel this with real content. Visiting professorship means that I'm supposed to visit you occasionally, so I really would like to do this as soon as possible, and I can promise you that this will happen in the very foreseeable future. Thank you very much.
Super, thank you. We invite you.
And thank you once again for your attention, and wish you all the best. Wish you all the best, and yeah, peaceful skies as soon as possible.
Thank you very much for your amazing lecture. You gathered together today physicists, chemists, biologists, material scientists, and a lot of other scientists in Ukraine. And thank you again for your support.
Thank you. Thank you. Thank you so much.
Thanks.
Bye-bye. Thank you.
Bye.
Thank you.